Hello, my dear friends. So, today we will start the new energetic subject of the physics, and we know which one is the energetic subject in physics, that is nothing but the quantum mechanics. And from today we will start this new subject, quantum mechanics, and with the point that is origin of quantum mechanics. How starts the quantum mechanics? Why the starting of the quantum mechanics? What are the limitations on the classical mechanics and originates of the quantum mechanics for the physicist and this our society? So, we will start with the subject physics and which branches at that time exist for the researchers and our physical society. At that time, classical mechanics, electromagnetic theory and thermodynamics, these three branches are the main focused branches in the subject of physics. At the end of the 19th century and the beginning of the 20th century, the quantum mechanics was originated at that time. But before that, classical mechanics is the main branch of our physics, and everyone is doing research in that field, that is classical mechanics, electromagnetic theory and thermodynamics. In classical mechanics, we have studied the Lagrangian equation of the motions, that is the study is regarding the particles which can seen by our eyes, that is the dynamics of matter. Lagrangian equation, then Newtonian mechanics, that is nothing but the laws of motions given by the Newtons, then Kepler's law and all about all theories regarding the particle or the dynamics of matter. In electromagnetic theory, Maxwell have developed this area of our physics, that is the electromagnetic theory, that has been developed by the Maxwell equation, that and we know that are the equations, that is the del cross E, del dot B, and we know that all, that is the properties of the radiation studied in the electromagnetic theory. And number third, that is the thermodynamics, that is the branch of statistical mechanics. We know that we studied this thermodynamics in statistical mechanics also, and in thermodynamics we studied the interactions of matter and radiation in that particular era of our physics. Then we have that subjects, then why it needs to develop the quantum mechanics? What are the limitations on these branches of the physics? So, in 1900 or at the end of the century of 19th and the beginning of the 20th century, Sir Max Planck at the year of 1900, Max Planck have described the phenomena of the black body radiation. In black body radiation, what he described? He described that while we hitting the any solid material, then that material changes its color, that is first it has the black. If we heated that material, then it originates this color, that is the red, after that yellow, after that white. But this phenomena we cannot explain by using the classical mechanics or other subjects. Then after that, Sir Einstein do the experiments of photoelectric effect. In photoelectric effect, that is phenomena related to the wave nature. After that, Rutherford atomic model, Bohr atomic model, then Compton effect, these are some examples where classical mechanics was failed to explain these phenomena at that time, and that phenomena very well explained by the our very famous subject, that is the quantum mechanics. Now, first, the classical mechanics fails to explain the relativistic behavior and microscopic behavior. We classified that is between two eras, that is first one is the relativistic behavior and second one is the microscopic behavior. In relativistic behavior, we studied what are the relativistic and what are the examples of non-relativistic, and in microscopic behavior we will explain the black body radiation, photoelectric effect, then Compton effect and so on. So, we will start with the relativistic behavior. Suppose one particle which has the mass m naught and it travels with the velocity, that is v, and which is equals to the speed of light, that is equals to c. Then m is equals to gamma m naught, where the gamma is equals to 1 by under root 1 minus v square by c square. But here we derived explain the nu is equals to c, that is the velocity is equals to the velocity of the speed of light. We have already seen that total energy E is equals to T plus E naught, that is nothing but the total energy is equals to kinetic energy plus rest mass energy for the relativistic behavior, and this is the particle m naught which travels with the velocity v, which is equals to speed of the light, that is 3 into 10 to the power 8 meter per second. Now, here we gave two examples, that is for the relativistic mechanics and non-relativistic mechanics, and there is a condition for the relativistic mechanics and also for the non-relativistic mechanics related to the kinetic energy and rest mass energy. If T is very much greater than the E naught, that means the kinetic energy is very much greater than the rest mass energy, and that is the example of relativistic mechanics. This is the condition for the relativistic mechanics. An example of relativistic mechanics, that is the electron. And for the non-relativistic mechanics, the condition is T is very much less than the E naught, means the kinetic energy is very much less than the rest mass energy. And example of this, that non-relativistic mechanics is the human body. This one part for the relativistic behavior, and another part for the microscopic behavior. That in that microscopic behavior we have to explain the black body radiation, then photoelectric effect, then Compton effect. But today we give only the introduction of this two effects, that is the photoelectric effect and the Compton effect. In photoelectric effect, we incident the light. In photoelectric effect, we incident the light, and in Compton effect, we incident the X-ray. We incident X-ray. See, here light, here we have used the X-ray. Then in photoelectric effect, here the emitted the electron, and we find the equation, that is k is equals to h nu minus phi, that is the kinetic energy is equals to h, that is the Planck's constant, nu is the frequency and phi is the work function. And here we will find the work function from this effect, that is the photoelectric effect. And in Compton effect, we incident the X-ray, and this electron, that is the free electron, one which is the scattered electron and another is the recoil electron, with the two different angles, scattered electron with the phi angle and the recoil electron with the theta angle. And we will find in this equation, that is the wavelength, that is the difference between wavelength, that is the delta lambda is equals to h by m naught c 1 minus cos phi. And we will discuss these microscopic behavior, that is the black body radiation, photoelectric effect, Compton effect, one by one on next lectures. Today we will discuss all about the origin of quantum mechanics, and in tomorrow's lecture we will discuss the black body radiation in detail. So thank you for watching this video and also subscribe our channel.